Good afternoon, everyone. So I'm recording this session. So just don't switch on your camera if you don't want to appear. I will see if I will switch off my camera because of the internet probably. And then so let me also mention a question that I had about the note. So the note, so the way I work is I have chapter 1, a note, for example. Once I finish chapter 1, then I will give you the note. So then I expect to finish chapter 1 Wednesday. So Wednesday I will upload the all note of chapter 1 because sometimes when I'm explaining or explaining the lecture. I make some additions to the note, so I prefer to give you the note at the end of each chapter. So I will upload the note of the whole chapter on Wednesday, inshallah. So now let's continue. So what we started, as I mentioned, just to what we are doing, we are trying to develop or calculate or derive the expressions of several electrical properties of materials. We are starting with general materials like a metal. For the moment, what we are doing, we are using classical mechanics, Newton's laws. We will use also Maxwell's equation. Yesterday, we took a copper cable, for example, and we apply an electric field to this cable or a potential difference. And then we calculated one of the most important parameters, which is the drift velocity and the mobility of electrons. Okay, so now another important quantity in electricity is the current density. So we also want to calculate the current. Can anyone remind me about the current density? What is the definition of the current density? Do you remember? We have seen this in physics 2. We have seen this in physics 222 also. Any?
The amount of charges traveling in a certain area, right?
Yes. So the amount of charges flowing through an area. So basically what we want to do, if I have, let's say an area here, this is an area. I want to know this area. I want to know how many charges. So the current density is actually, it's a vector. It's the number of charges. Well, actually, it's the, it's the number of charges per second per area. Okay, and this number of charges per second, what is the number of charges per second? What do we call it per time?
It's current,
Exactly.
right?
Yeah, it's electrical current, electrical. Okay. Yeah, so that's very good. So J will be the number of charges per second per square meter. So what we want to do, yes, question? Any question? Okay, so so I want to calculate the current density, which means I want to calculate the number of charges. Well, the number of charges is just the charge of one electron times the number of electrons flowing this area. Okay, so I know that the number of electrons per, let's define Ne is the electron density. Electron density. Each material has an electron density. What is the electron density? Is the number of electrons per volume. Okay. So the number of electrons per volume so this NE, if I want to calculate the number of electrons per area, okay, if I want to calculate the number of electrons per area, it's equal to the number of electrons, the density, times the delta x. Delta x is the distance traveled by these electrons during delta t. So the number of electrons per area is just the number of electrons per volume times delta x. Okay, are you following? And we know that delta x is equal to delta t times, which parameter is here? The distance traveled by the electron during delta t is equal to what I should write?
Velocity.
The drift velocity. Exactly, the drift velocity. So this means that it's equal to the electron density, which is given always, and then the drift velocity, and then delta t. Okay, so then the number of electrons per area per delta t per time is equal to NE VD. So what do I want at the beginning? I wanted this. I wanted the number of charges. This is what I wanted at the beginning. The number of charges per second per area. So here I have the number of electrons per area per second, right? What do I want to do here to get the current density? I want to multiply by what? I have the number of electrons per area per time. And I want the number of charges. All what I have to do is to multiply by
E.
the charge of one electron. Yeah, by the charge of one electron. And this will give me the the electric current density. So the electric current density will be equal to NE, which is the density of electrons, of free electrons, times E, electric charge, times the drift velocity. So NE, please don't forget, is the electron density or the density of free electrons. Density of free electrons. Free electrons means the density of electrons that can move. They can move. And of course, the unit is ampere. Is ampere per meter squared. Any question?
Wait, so the NE is the free electron density, right? Is that what you
Yes.
said?
Yes.
Just right now?
So, yeah, it will be per cubic meter. Yeah, the free electron density, or the density of free electrons. The density of free electrons. Any question? So now I know that this is NE, this is E. I know that the drift velocity is equal to the electric charge times tau divided by m, the electric field. Who can remind me what is tau?
It's the average time between two collisions.
Exactly. So yesterday, what I did not mention here, tau is the average time between two collisions. It is also called relaxation time. Relaxation time. So it is also called relaxation time, or the mean free time. The mean free time. So it has three. The mean free time, which is the average time the electron is free. It does not conduct any collision. Okay. So let's replace the drift velocity with each value. It is equal to E tau over log if you are not talking, please mute so that I can. Okay. Okay. So the current density is equal to the number of electrons, the free electrons per cubic meters, the charge of the electrons, the relaxation time, the mass of the electron, the electric field. So this is equal to Ne times the charge tau over ME. Okay. Now, this quantity is, have you seen this kind of quantity? The current density is proportional to electric field. This is called conductivity. This is the conductivity of the material, the conductivity. Now, this is really the Ohm's law, is conductivity is equal to the current density divided by the electric field. The current density divided by the electric field, okay? So now, the conductivity, the unit of the conductivity is 1 over ohm meters, or Siemens per meter, because Siemens is ohm minus 1. Any question? Okay. Now, we also know that the mobility is equal to E tau over M. We can also express the current density, the conductivity as, so the conductivity is equal to N E squared tau over M. It can also be N, number of electrons, E, and the mobility. This is another equation for the mobility, for the conductivity. So the conductivity has this expression, and it has also this expression. Any question? So the conductivity of copper, just to give you an example, is 5.9 10 to the power of 5 Siemens per meter. Okay, the conductivity of salt and ACl is 210 to the minus 6 Siemens per meter. So you can see, of course, the conductivity of the semiconductor. So copper is a metal, conductivity is high. NaCl is almost an insulator. The conductivity is very low. Silicon is a semiconductor. We will talk about it later. It still has a bad conductivity. Okay. Any question? So we define the drift velocity. We define the current density. We define the mobility of electrons, and we define the conductivity. Those are the main electrical parameters that we are defining for a metal, for example. Okay. Okay. So just remember this, please. This is very important. Okay. Now, let's give an example. Let's give an example. Let's consider copper. Copper with a valence 1. I will tell you what is the meaning of the valence. But so the copper has a density. Copper has a density of 8 rho is equal to 8.69 gram per cubic centimeter. And copper has conductivity of 5.98 10 to the power 5 per meters, okay? And then it has also atomic mass, and the atomic mass is 63.4 gram per mole. So this is copper. The question I have here is, first is calculate the mobility of electrons in copper. B, if we apply a potential difference delta V of 10 volt in 100 centimeters of copper cable, what is the drift velocity of this electrons? Okay. Now I want to calculate the mobility of electrons in copper. So what is the mobility? Yes, the conductivity is given. So we know that the mobility is equal to, which equation we did? We saw that sigma, the conductivity, is equal to the mobility, electron charge, the number of electrons, the free electrons. So the mobility will be equal to the sigma, the conductivity, divided by the electron charge and the number of electrons. Are you following? Are you following?
Yes.
Yes, Professor.
Okay, so now, question for you. I want to calculate the mobility. I have the conductivity. I have the electron charge, 1.610 to the minus 19. I don't have this, and I don't have this. Well, in order to calculate, there is no other way. In order to calculate the number of electrons, in order to calculate the mobility, I have to calculate the number of electrons. What is the number of electrons? The density of electrons. The density of electrons is the number of electrons divided by volume, per volume. Please, here I want to mention something. What is the valence? The valence of copper is equal 1. The valence of copper means that each atom will give 1 electron. Okay, which atom will give 1 electron? It's like Cu plus. So if I tell you the valence is 2, this means each atom will give 2 electrons. What do I have to do now? I have to calculate the number of atoms per volume, and I know that each atom will give me an electron. So the number of electrons will be the same as the number of atoms per volume. Now, this is a high school question and also a first-year chemistry question. So I'm talking about the number of atoms per volume in copper. Okay. So how do I solve this problem? I can solve it as follow: number of atoms. Any idea? Any idea? I'm giving you the density of copper, atomic mass of copper, and I'm asking you to calculate how many atoms in a cubic meter do we have, or cubic centimeter? How many atoms of copper? How do you solve this? You think
Won't
this?
you multiply the atomic mass with density?
Okay, Okay, so you want to, so what do you want to do? You want to calculate the following. You want to do the number of atoms per mole, and in mole, 1 mole, how many grams, and in grams, how many volume. So in other words, the number of atoms in a volume. This is what I want. Okay. The first thing I want to do is how many grams in cubic centimeters. And then 1 gram, or how many moles in 1 gram. And this will give me the, so then if I want to calculate the number of atoms in volume, I want to calculate the number of atoms in 1 mole. How many atoms do we have in 1 mole? Any atom. How many atoms do we have in 1 mole? If you take any atom, how many atoms do you have in 1 mole? In 1 mole of iron, in 1 mole, it's the same number. You have seen it in high school.
Is you're to 6 point Avogadro's constant, right?
So the Avogadro number.
Is it 6? Yeah.
Right? Okay. Now, how many mole per gram? Mole per gram is 1 over the density, atomic mass. So it's 1 over atomic mass. And how many gram per volume is the density? So this is how you calculate. Please remember this. You want to calculate the number of atoms per volume. What you have to do first, how many atoms in 1 mole? And how many moles in 1 mole, how many grams? In 1 gram, how many volume? Okay. So it's the Avogadro number, 60.22 10 to the power of 23 atoms, times 1 over atomic mass. Well, atomic mass is 63.4 gram per mole, times the density. The density is 869 gram per cubic meters. Now, I would like to convert everything. Any question, please, here? Do you have a question? Please remember this, or at least understand this, because this is something that comes very often in quiz and in exams. If you want to calculate the number of electrons or atoms in one in cubic meters or cubic centimeters. So here the answer is 8.447 10 to the power of 22 per cubic centimeters electrons. This is the density of free electrons. Any question, please?
Professor, can you please start from the atomic mass of the mole?
So from here?
Like if we have enough questions asking us to get from the valence and from the density, or like how can I use this formula?
This formula?
Yeah.
For example, well, this formula is straightforward. In this question, in this problem, I asked you to calculate the mobility of electrons, right?
No, I mean the second one. I got the mobility one. The NE.
Yes, yes. No, please go
the
ahead.
number of. I mean the second formula. I've got the mobility, but I didn't got the number of atoms over the mole, and I can.
Yeah, okay.
Yeah,
So yes. Okay. So let me add one page so that I can explain it. I want to calculate the number of atoms in per cubic centimeters. This is I want. I want in 1 cubic centimeters, how many atoms do I have, right? This is what I want. So the first thing I want to calculate how many atoms do we have in this volume in cubic centimeters. I know that in copper, for example, I know that in copper, I have 63.4 grams in 1 mole, right? In 1 mole, I have 1 mole of copper weight 63.4 gram. And I know this means that 63.4 grams is correspond to 6.02 10 to the power of 22 atoms of copper, because this is 1 mole is Avogadro number, right? Are you following?
yes.
Okay. So now what I want to know, I know that this amount of atoms weight this. But what I don't know is the following is how many in 1 volume, how many grams in 1 cubic centimeter, in how many grams do we have in 1 cubic centimeters? But I know that in 8.96 grams in cubic centimeters. I know that 1 cubic centimeters of copper has a mass of 8.96 grams. And I have this. So I have these two ones. Let me explain it here. I know that in 8.96 gram of copper, 1 cubic centimeter of copper has a mass of 8.96 gram. And I know that in 63.4 gram, I have 6.02 atoms of copper. So what I want to know how many atoms in cubic centimeters. What do I have to do?
I divide by 8.96.
Yeah, so I divide 6.02 10 to the power 22, multiply by 8.96 divided by 63.4, right? Right?
Yeah.
So that's what I did. That is clear, exactly what I did here. So 6 times 8.69 divided by 63.4. Okay, so you start by calculating, you want to calculate the number. So you want to calculate the number of atoms in cubic centimeter. You know that in 1 mole, you have 63 grams, which means that amount of electrons, they have a mass of 63 grams. But you know that 1 cubic centimeter has this amount. Now you want to know in 1 cubic centimeter how many atoms. So all what you have to do is this divided by this. Is this clear?
It's clear.
Thank you. Okay. So now this is in So we have just calculated this. Now the mobility of electrons, is equal to sigma divided by the number of atoms of electrons, free electrons, times the charge. What is sigma? Sigma was given, right? Yes, sigma is given here. Sigma was given, which is equal to 5.98 10 to the power of 5 Siemens per meter. What should I do then? What is the next step?
Just plug it in.
Okay, so I have to plug in. Okay, let's plug. But this is, yeah, it's very easy. We have to plug. But remember, please, this is in meters. And this is in cubic centimeters. Before plugging it, you need to convert everything to meters, for example. Now, I have a question for you. Here is I can tell you one of the mistakes that students have. I have 8.47 10 to the power of 22 electrons per cubic centimeters. If I want to convert or to calculate per cubic meters, what do I have to do? If I have, okay, so
10 to the power of 6.
sorry there.
10 to the power of 6. Or
Yeah.
3.
So 10 to, what do I have to do with 10 to the power of 6?
Divide or
Well, this is the
Divide.
this is the question. This is the question. This is the question sometimes that I have a student in the exam. Sir, do I have to divide or multiply? Well, what do you think?
Multiply.
Multiply. Did you
Multiply.
understand why multiply?
Because normally from centimeter cube to meter cube you have to divide it, but since centimeter cube is on the denominator, so it just goes up.
Let me, yeah. So sometimes it would be nice to explain it. Yes, maybe everyone knows about it, but let me just explain it with a very simple high school method. This is 1 centimeter. Let's say this is just 1 centimeter cube, okay? If I have 1 electron per cubic centimeters, let's assume I have 1 electron per cubic centimeter. How many I will have within cubic meters? I know in each cubic centimeter, I have 1 electron. It is clear if I go to cubic meters, I will have a huge number. And this huge number is 10 to the power of 6 and multiply by 10 to the power of 6. All right, do you agree? Hello? Is it clear for everyone?
Yes.
If I have 1 electron in 1 cubic centimeter, if I go to a larger volume, of course, it will increase. So I have to multiply. Now, what is the conversion factor? We know that 1 cubic centimeter, 1 centimeter is 10 to the minus 2, okay? 10 to the minus 2. Or 1 meter is 100 centimeters. So 1 square meter is 10 to the power of 4. 1 cubic meter, 10 to the power of 6. Please don't forget this. So yes, so this number will become 8.47 10 to the power of 28 electrons per cubic meter. Then you can do the calculation. So here it's 8.47 10 to the power of 28 times the number of the charge of the electron. And then you can do the calculation. Obviously, the calculation will be cubic meters volt per second, whatever you find here. Second question. Now we calculated the mobility. Now, what is the drift velocity? Drift velocity is equal to the mobility times the electron. And if you remember, I give you, if I apply a potential difference of 10 volt over 1 meter. So it's very easy. The electric field will be the delta V divided by L, which is mobility that we found here, times delta V10, so mobility divided by 1, because it's in meters. So it's a straightforward question. Okay, any question?
Professor,
Yes?
for A, is it fine if we converted conductivity to centimeters instead of the
Yes.
number of
Yeah, no
electrons?
problem. But please try to understand the conversion. The reason is sometimes I will ask you, give me the mobility in meters squared per volume, per volt second. Just to understand. Okay?
Okay.
Okay. Okay, so then we go to something. Any question? So then so remember, we are calculating electrical properties of materials. As I mentioned, we calculated the drift velocity, mobility of electrons, the collision, relaxation time, and sigma. Okay, and obviously the number of electrons, the current density. So those are the parameters that we calculated. Obviously, sigma is the conductivity. There is also resistivity. And the resistivity is just 1 over sigma. Okay. Now, we can also, if you remember, we have seen that for a metal, the resistivity as a function of temperature is equal to 1 plus alpha T minus T0. So this you have seen in physics 207. This is the dependency on the resistivity of the resistivity on the temperature. Now, if I have, if I apply potential difference here, delta V, okay, and I have this metal, for example, has a certain resistivity. What happens when I apply when I increase the temperature? What happens to the resistivity when I increase the temperature? If I increase the temperature, what happens to the conductivity of a metal? Hello? If I take a metal and I measure its conductivity, okay? What is conductivity? Can you tell me what is the meaning of the conductivity? Who can tell me the conductivity? What is the meaning of the conductivity?
Ability of like current flow, so like
Exactly. So the ability to conduct current. Now, what will happen to the conductivity of the metal, copper, for example, if I heat it? Does it increase or decrease or stays the same? It doesn't depend on the temperature.
the conductivity would increase, right?
Okay. So let's make some common sense here. I have an electron that is moving here. When I increase the temperature, the molecules start moving around randomly. So the electrons start colliding more and more, which means the flow of electron will slow down. So the conductivity will slow down, and this is already seen here. The resistivity is increasing as a function of the temperature. Please remember this. For a metal, as a function of temperature, the resistivity increases. This is the resistivity. And the conductivity decreases. Is this clear, please?
Yes.
Please remember this, because we will see that in semiconductors, it's the opposite. But please remember this. Oh, so this is very important quantity, that the temperature affect the electrical properties of a metal, and it deteriorates the electrical properties of a metal. Okay, so let's go to the next slide. Next part. We can also calculate some parameters using the what we call hydrodynamic flow. Hydrodynamic electron flow. So what is this? If you remember what we said, we mentioned the following. We took a copper cable or a metal cable, we apply an electric field, let's say this way, and I have an electron moving, and then we apply, in the first part, we apply F equal ma, the electric force, and then we derive the drift velocity and so on, right? This is what we did. We can also do the analogy with a fluid, what you use the fluid mechanics. When a fluid is moving, this fluid will have some, or any flow will have some resistance, friction force, and when the electron is moving, the electron is subject to two things. It's subject to the electric force, but it's also subject to a resistance force, a friction force. Where this friction force is coming from? Where this friction force is coming from?
The molecules inside the metal?
Exactly. It's like, look, it's like if you are moving in a tunnel with a lot of people. So you will not be able to run, because when you run, you start colliding with people. So this is a friction. It will slow down your motion. So how do we do this? We can apply F equal ma. So the mass times the drift velocity, this is F equal ma, is equal to the force of the electrons, the electric force due to the electric field, minus the friction force, which is m, all friction force in fluid mechanics, friction force, they are modeled. So the friction forces, they are modeled by a quantity that is opposite to, proportional to the momentum. Okay, so this is a friction constant or friction coefficient. Okay, so you can do the same thing, mv. Okay, so, and what is this? This is just the electric force minus because it is a friction, so it's opposed to the motion, and this is a coefficient of friction, and v. Sorry, this should be. Now we can easily see that this is a differential equations. The drift velocity divided by, with respect to dt, plus zeta v, okay, is equal to E over ME. This is drift velocity. This is just a differential equations of the type that you have seen in calculus, which is f prime plus AF is equal to K. Okay, and the solution of this F or V here is equal to EM zeta 1 minus exponential minus T zeta. And you can easily see that zeta from here, because the exponent argument should be dimensionless. So this has a unit of 1 over time. So zeta is exactly 1 over the collision time. Okay. So the drift velocity then becomes E over M tau, and then 1 minus T over tau. Now, when the flow is continuous at steady state regime, T goes to infinity, which means exponential minus T over tau goes to 0. Then I get the drift velocity that we got already before, which is E tau over M E. And what is this? What is this quantity?
Mobility.
Exactly. So the mobility. So you can see just using very simple classical mechanics, F equal ma, you can calculate the electrical properties of a metal, like drift velocity, conductivity, resistivity, current density, of course, current, and all these parameters. So this is a very easy step. Later, we will see that there are several parameters that we cannot use, we cannot calculate using classical mechanics, and that's why we will go for quantum mechanics. Any question?
Professor, so here we use the F equal ma to find what exactly?
Yeah, so here we use F equal ma. The difference between there and here, the first part and second part, here we use F equal ma by including friction force. Before, we used F equal ma by including the average drift velocity. If you remember, we said that the A is equal, or the drift velocity is equal to the acceleration times the collision time. Okay? This is what we used before. Okay?
Professor?
Yes.
I don't understand what's the F dash plus AF equals to again?
So, can you just, I think someone is knocking on the door. Just give me 10 seconds, please.
Sure.
Thank you. Okay, so the question was, can you hear me?
Yes.
Okay, so the question was, you did not understand this one, right?
Yes.
Okay, let me open another page. So what we did, we calculated the following. Did you understand how we end up with plus zeta V is equal to E over ME? Did you understand this?
Yes.
So this we calculated in a very small steps, right? What is this? This is the derivative of the drift velocity, right?
Yes.
This is the first derivative. And this is the drift velocity. Right?
Yes, you're right.
So this is similar to a differential equations that you have seen where you have a function, the first derivative, which is this one, plus a constant, any constant, I call it A, which is zeta in this case, times the function itself is equal to another constant. Did you understand this?
Oh, okay, yeah. I understand, yeah.
And this you have seen in calculus that it's very simple equation. You can easily derive it using very simple steps. So all what I'm trying to tell you that this equation is a differential equation of first order that we can solve, right?
Yeah, makes sense.
Okay. Okay, so let's go to something else. I will start here what we call the Hall effect. Hall effect is very important, but first thing I want to do is to a cross product, to talk a little bit about cross product. I hope you remember the cross product. And the cross product, the magnetic force. Let's talk about the magnetic force on a charge, on a moving charge. On a moving charge. Okay. Now I have a question for you. If I have let's say a positive charge plus Q moving this way with a velocity V, and I apply a magnetic field here, in which direction will the charge move? In which direction will the magnetic force, remember the magnetic force is Q V cross B. In which direction the magnetic force will be?
Is it out of the page?
Sorry?
Out of the page?
Okay, I have an answer out of the page. Do you agree with Noor? Noor, right?
Yes.
Yes. Do you agree with Noor? Well, either you agree or disagree. So you cannot. Any other question? Any other suggestion? Wow. Well, if you don't understand, you have to tell me. Yes, Noor, you are correct. It's out of the page. Okay, so it is out of the page. So the magnetic force, yeah, you are correct. You are right. Okay, the magnetic force will be out of the page. Now, I will give you also another question. So if I have now an electron, now it is an electron, a negative charge, and I have a magnetic field inside the page. So the electron is moving upward. The magnetic field is inside the page. Okay. In which direction will the force exerted on the electron be?
Towards left.
I did not understand. Toward?
Towards left, right? Like left side.
Any other suggestion? Do you agree with the who spoke?
Me, Professor.
Yeah, me who Omer?
Yes.
Okay. So it's Ahmed or Omer?
Omer.
Okay. Because I sometimes the last name is written the first name. Yeah. Okay. Who well, I have 7 students, so I should have an answer from 6 people at least. So Omer has said that to the left. Do you agree? Okay. Should I start calling you by name to agree or disagree? Omer, why did you say to the left?
I used the right hand rule, Professor.
Yeah. So you use the
used-
right-hand rule, but you forgot that the electron has a negative charge.
Oh yeah.
So yes,
Yeah,
it should be to the right.
yeah, you're right. It's right now. Yeah.
So please, the rest of the class, I'm a little bit worried. You did not answer. This means 2 things. Either you are not following, which at least I know that Noor is following because she is answering my questions, or you did not understand. If you are not following, please follow. If you did not understand, tell me. Because this is very important. I didn't want to start the whole effect. The whole effect is about magnetic field. If you don't understand this, tell me. If not, I will stop here and I will start tomorrow the whole effect. I have a question for all of you. So let me first stop the first thing because here I will stop recording.